We have now the determinants and elementary operations. Recall that in our previous discussion, we introduced the cofactor expansion to find the determinant of a matrix. However, using such method in a matrix of order 4 or higher would be a bit messy. So this time, we will discuss a different approach in finding the determinant which uses elementary operations. So let us start with the effects of elementary row operations on a determinant. So we have let A and B be square matrices. If B is obtained from A by interchanging two rows of A, then the determinant of B, which is the new matrix obtained, is equal to the negative of the determinant of A, which is our original matrix. Also, if B is obtained from A by adding a multiple of a row of A to another row of A, then the determinant of B is just equal to the determinant of A. So this elementary row operation doesn't change the determinant. And for the third one, if B is obtained from A by multiplying a row of A by a non-zero constant C, then the determinant of the new matrix B is equal to that constant C times the determinant of the original matrix A. For example, we have the matrix B is obtained from A by interchanging rows of A. So we have here row 1 and row 2, but in this case, we have now 1, 4 here and then 2, negative 3. So interchange rows 1 and 2. Now, if we are going to evaluate the determinant of this, so we multiply this 2, we have the diagonal minus the product of this. So that's 2 times 4, 8, and then minus negative 3, so that would be 11. And on the other hand, if we solve for the determinant of this, we multiply these two. We have 1 times negative 3, so that's negative 3 minus 8, so we have negative 11. Observe that the determinant of B is the negative of the determinant of A. So that is how we illustrate this first item in this theorem. Now, next, so we have the matrix B, which is obtained from A by adding negative 2 times the first row of A to the second row of A. So again, this row is multiplied by negative 2 and then added to this row to get new row 2. So we obtain this matrix. Now if we get the determinant of this, we have 2. And then for matrix B, the determinant is also 2. So the determinant of this original matrix and the new matrix, which is formed by adding a multiple of a row of this to another row, then the determinant is just equal to the original one. And for the third example, we have matrix B is obtained from A by multiplying the first row of A by 1/2. So we have 2 negative 8 here. We multiply by 1/2, so that becomes 1 negative 4. And take note, if we get the determinant of A of this is equal to 2, and the determinant of this is 1. Okay, so again, the determinant of this new matrix obtained is equal to 1/2 of the determinant of the original matrix, because this is obtained by multiplying the first row of A by 1/2. Now, let us show how to find a determinant using elementary row operations. So, given this matrix A, what we are going to do is we rewrite this matrix in triangular form while applying the theorems we introduced to find the determinant. So in this particular given, we prefer to rewrite this into an upper triangular form or the upper triangular matrix, since we have already 0 here below the main diagonal. So the determinant of A is have 2, negative 3, 10, 1, 2, negative 2, 0, 1, negative 3. Now, first, we interchange rows 1 and 2, but again, take note how this will affect the determinant of this given matrix. So we have, so from the theorem, interchanging two rows of A will negate the determinant of the new matrix, or the negative of the new matrix equals the determinant of the original. So we will put here the negative and then interchange first and second rows. Okay, and then next we can maybe we can interchange also rows 2 and 3, so that we will have 0 below this one here, and then we will have a leading one. So again, interchanging two rows will negate the determinant, so that's negative, and then another negative that will become now positive. So we have 1, 2, negative 2, 0, 1, negative 3, and then 2, negative 3, 10. Next, we will make this 0. So we can do that by multiplying first row by negative 2, and then we add it to row 3, so that we will have a new row 3. But again, this operation, row operation, will not change the determinant of the given matrix. So we'll have, so multiply by negative 2 and then plus 2, that's 0. We multiply this by negative 2 plus negative 3, so that's negative 7. This is 4, and then we have 14. Okay, and the next, we have here negative 7. So we'll make this 0 by multiplying row 2 by 7, and then we add it to row 3. Now again, that operation will not change the determinant. So we have, sorry, that's negative 3, and then we multiply this by 7 and then add, so that's 0. We multiply this by 7, so that's negative 1, negative 21 rather, plus 14, so that is 7. Okay, so recall that the determinant of a triangular matrix is just equal to the product of the entries of the main diagonal. So we have 1 times 1 times 7. So therefore, the determinant is 7. Okay. Oops. Sorry, we have here some error. That is, we multiply this by 7. So this must be negative 21 plus 14. So this must be negative 7. So we have here negative 7 instead. So 1 times 1 times negative 7. So the determinant of matrix A is negative 7, not positive 7. Next, operations performed on the columns rather than the rows of a matrix are called elementary column operations. And two matrices are called column equivalent if one can be obtained from the other by elementary column operations. The theorems remain valid for elementary column operations. So we can also apply what we have learned so far to the columns of the matrix instead of the rows. For example, in here, we interchange columns 1 and 2. And so we get the negative of the determinant of this matrix. So we apply the same theorem that we have discussed for the row operation. Next, we have here column 1 is multiplied by 1/2. So we have this. column 1 rather. So we have column 1 multiplied by 1/2, so that becomes 1, 2, and then negative 1. So the determinant of this times 1/2 is equal to the determinant of this new matrix. Or simply, we multiply the determinant of this by 2 so that it is equal to the determinant of the original matrix. So we applied number 3 of the given theorem previously. Next, we have here the conditions that yield zero determinant. If A is a square matrix and any one of the following conditions is true, then the determinant of A is equal to 0. So for the first condition, an entire row or an entire column consists of zeros. So this condition will yield to a determinant 0. For example, this matrix has zeros entirely on the first row, so its determinant is 0. This is because if we apply the cofactor expansion and choose row 1, so expansion in row 1, then we will just get 0 since each cofactor in the given expansion or the expansion will be multiplied by 0. Next condition, the determinant is 0 if two rows or columns are equal. For example, here we have rows 1 and 3 are equal. Thus, the determinant of this matrix is also 0. Since if we multiply row 1 by negative 1 and add to row 3, then it will yield a new row 3 which will consist entirely of 0. So that would be just the same with the first condition. So the determinant is 0. And for the third condition, we have the determinant is 0 if one row or column is a multiple of another row or column. For example, we have that. So here, observe that column 3 can be obtained by multiplying column 1 by negative 3. So that's negative 3 times negative 3, we have negative 6 times negative 3, we have positive 6. Again, applying elementary applying elementary column operation here will yield a column consisting entirely of 0. So if we multiply this by negative 3 and then add to this column, then it will yield to a new column 3 consisting entirely of 0. Now, let us have more examples in finding the determinant. So find the determinant of this 3 by 3 matrix. So note that we can combine the elementary row or column operation with the cofactor expansion. For example, in here, so let us write the notation first. We have determinant of A is equal to the determinant of 5, 2, 2, negative 4, negative 1, negative 3, 0, 6. Okay, since we have already 1 0 in the third row, we can create another 0 on this row so that it would be easier to apply the expansion by cofactor. So to do this, we can multiply column 1 by 2 and add to column 3 to get new column 3. So we multiply this by 2 so that this becomes 0 here. Okay, so note that this particular elementary column operation will not change the determinant of the original matrix. So that would be just equal to, we have negative 3, 2, negative 3, 5, negative 4, 0. So we don't change columns 1 and 2. We have, again, we multiply by 2 this column and then add to column 3. So we have times 2, so that's negative 6. So we have plus 2, so that's negative 4 times 2, so that's 4 plus negative 1, that becomes 3 times 2, so that's negative 6 plus 6, so we have 0. From here, we can now apply the cofactor expansion in the third row. So we have the determinant of A is equal to, since again we have two zeros here, so we just need this entry here and then multiplied by negative 1 times this corresponds to position 31, A31. So this is in the third row, column 1. So that's 3 plus 1 times, if we delete this column and this row, we have these entries. So that is the minor, corresponding minor. And then we simplify. This becomes 4, so that's even. So this becomes positive here. So we have 5, negative 4, negative 4, 3. And recall how we get the determinant of a 2 by 2 matrix. So we just multiply the diagonals and then get the difference. This is 5 times 3 minus negative 4 times negative 4. So that's equal to negative 3. So this is 15. And then minus 16. So that's negative 1 equals positive 3. Therefore, the determinant of A is equal to 3. Next, let us find the determinant of this 5 by 5 matrix. We have A is equal to, determinant of A, we have 2, 0, 1, 3, negative 2, negative 2, 1, 3, 2, negative 1, 1, 0, negative 1, 2, 3, 3, negative 1, 2, 4, negative 3, and then 1, 1, 3, 2, 0. So we have here the 5 by 5 matrix A. So observe that in column 2, or the column 2 has most zeros. So we have 1, 2 zeros here. So we will try to create more zeros in this column, column 2. To do that, we can make these two entries here 0 by first using this row here. We can multiply, or we can add rows 2 and 4. So it will yield a 0 here. And then also for the last row, we can make the 0 by multiplying this by negative 1 and then add to row 5. Take note that those operations will not change the determinant of this original matrix. So we will just do both at one time. So we'll copy the first three rows there. So we have 2, negative 1, 1, 0, negative 1, rows 3. Okay, so what we want again is to make this 0. So we add rows 2 and 4 so that we will have a new row 4. So we add this, so that's 1. Then we add that's 0. We have 5. Add this, we have 6. And then we have negative 4. Also for row 5, we will multiply this by negative 1 and then add to row 5. So this becomes positive, so that's 3. We have 0, that's negative, so that becomes 0. Negative, so that's 0. And then we have negative 1 times negative 1, so that's positive 1. Now, since we only have one entry here, which is not 0 in this column, so we'll do the cofactor expansion in this column 2. So we will just need the entry 1 times negative 1 times, this is on the second row, and second column we multiply by, we delete this column 2 and row 2, so we will have here 2, you can delete this, we have 2 1 3 negative 2 1 negative 1 2 3 1 5 6 negative 4, and then 3 0 0 1 0. Now we have reduced the problem in finding a 5 by 5, the determinant of a 5 by 5 matrix into finding the determinant of a 4 by 4 matrix. Now since the last row, the fourth row, has the most zeros, so we will do the cofactor expansion in this row. So we can make this 0. So to do that, we can multiply this column by negative 3, and then we add to column 1. So that is, let us continue here. So that's equal to, so this is just 4, so that becomes positive. So the determinant will be just equal to, again, we will change this column. But remember that that column operation will not change the determinant of the matrix. So we'll write 5 0 3 2 6 0, and then negative 2 3 negative 4, then 1. Okay, so we will just change column 1 by multiplying column 4 by 3, and then we add it to column 1. So times 3, so that's times 3, that's negative 6 plus 2, so negative 4. We multiply this by 3, so that's 9, so that becomes 10. Am I right? So times, rather it should be times negative 3. Sorry. We multiply this by negative 3, so that's positive 6 plus 2, so this becomes 8, times negative 3 plus 1, so that's negative 8, and then times negative 3 here, so that's negative 12 plus 1, so that's 13, and then lastly that becomes 0. So again, we do the fourth row expansion using this. So we will have 1 using this entry times negative 1 times, this is in the fourth row, plus we have the fourth column, so that's 4 plus 4, times we delete these columns and column and row, so we have 8 1 3 negative 8 negative 1 2 13 5 6. Okay, so again, we have reduced our problem in finding the determinant of a 3 by 3 matrix. So let us continue. So again, sorry for that. So we have here the 3 by 3 matrix. So we can add these two so that it will yield 2 zeros here. So we have 0 0 5, and then we will do the first row expansion. So we'll use this. So we have 5, and then delete this row and column. So we have the remaining matrix. We have negative 8, negative 1, 13, and 5. Now we have a 2 by 2 matrix, so we apply the rule. We will multiply the diagonals and then get the difference. So that's 5, and then this is 4, so that's become positive. So we have here negative 8 times 5 minus 13 times negative 1. So that's negative 27, and then multiplied by 5, so that's negative 135. So we have now the determinant of A. So you practice by finding the determinant of these matrices. So that's the end of our chapter 2.2. We have the determinant and the elementary operations.